Hello and welcome to this presentation brought to you by Jackie, me, Vraj, and Dhruv. And what we will be talking about is singularity functions and their applications to mechanics of deformable solids. So we should start off with a quick introduction. You may be wondering, what is a singularity function? Well, a singularity function is basically just a class of discontinuous functions that contain singularities. And if you don't know what a singularity is, they're basically just discontinuities, a point in a function where the dependent variable, the y-axis, is not defined. So singularity functions are notated with the angle brackets. You see the pointy ones on the PowerPoint, and these are typically called singularity brackets. And once a function is notated with those brackets, one will know that it is a singularity function. Now, singularity functions are commonly used for static analysis to find the bending moments of a beam. And Macaulay brackets are basically just a notation used to describe the ramp function. And if you don't know what the ramp function is, it's basically when x is less than a, the y-axis, the output is just 0. And when x is greater than a, then it's basically not a 0 and it goes at a slope. And you can see the example on the slide right now. And the reason why people use Macaulay brackets is basically the Macaulay brackets provide an easy way to integrate these discontinuous curves. And by doing so, we can find the bending moments and angular deflection and other static properties of the beam. So when we use singularity functions, we use them mostly to find the moments and angular deflection when there is a discontinuity or discrete loading on the beam. And the reason why using singularity functions is so important is because engineers commonly use static analysis, especially when it comes to creating structures. And by finding these moments, the angular deflection, etc., uh, we can ensure that the system is stable and safe to use.
In the case of analyzing singularity functions, three foundational topics need to be discussed prior to diving into the subject. The three being the concept of bending moment, shear stress, and a little more background knowledge on what singularity functions are and the importance. Let's start by looking at bending moment. Bending moment is quite literally the measure of how much an object bends or deforms in that sense due to an external force or moment. A common element that is looked at for the effects of bending are beams, which can be loaded at any point along the length. This effect can lead to failure in an element, although there are scenarios that need to be considered. One being that a shear force may lead to a failure before the bending moment can. The other being that a structure may end up pivoting or rotating about a point if it is not appropriately restrained. The bending moment is directly proportional to the force being acted upon a point and the radius between the point of force and the point of the support. Knowing this, the equation can be derived where the bending moment is equivalent to force multiplied by the radius. Now let's switch focus and look at shear stress. Shear stress is when parallel layers of a structure slide against each other. This phenomenon can be seen in something like graphite pencils. Sheets of carbon are sheared off of the main piece and are left behind on the paper, thus allowing us to write. The equation for shear force is as follows. Tau equals force over area. Finally, let's briefly look into the significance of singularity functions and the rules of integration. Although the significance of singularity functions is already explained, let's clarify that a little bit. Looking at the figure, it can be observed how multiple discontinued loads result in having to find multiple individual moments and stresses. Having to do all these calculations repeatedly is redundant, and using singularity functions, all these operations can be done in one equation. Now, looking at the integration rules on the right, there are really only two. When n is greater than or equal to 0, and when n is less than 0. For the case when n is less than 0, integrating the singularity function results in n plus 1 as the power. But when n is greater than or equal to 0, we need to add a coefficient of 1 over n plus 1.
Next, I'll be going over the concepts related to this topic, specifically covering creating force-based diagrams for a given problem and using them to create a loading function, and then through integration, devising equations for bending and shear moments. To do this, we'll look at the most basic distributed loading examples. To begin, it is important to understand why singularity functions can be used to describe loadings. Here we have a very simple beam, which is defined by red, and the blue is the deflected shape of the beam, or the elastic curve defined by Ex. So this is a very simple example, and if we take the derivative of the elastic curve, we get its slope. Now, when we take the second derivative of the elastic curve, or the derivative of the slope, we get the curvature, and we know that the curvature is defined as the bending moment over EI, which is the flexural rigidity. Similarly, if we continue to take derivatives, the derivative of the moment will be the shear function, and so we get the shear moment over EI, and if we take its derivative once again, we get the loading function. The purpose of what I showed here is to show that given a loading function, which can be defined using singularity functions for a given problem, we can take the integral to determine the shear moment and then the double integral to determine the bending moment, which will also be equations using singularities. Next, I would like to show the 4 basic loading cases and the general form of its loading equation, and through integration, the bending moment and shear force also. Here, our first example is a concentrated moment at a specific location defined by A. In this case, our loading function will be W of x is equivalent to MO multiplied by x minus A in singularity brackets raised to the power of negative 2, where MO is the moment and A is the location. This loading function can then be used to determine the shear force function by taking its integral. Here, then we get the shear function as V of x is equivalent to the integral of the loading function, which will be MO multiplied by x minus A in singularity brackets raised to the power of negative 1. And integrating once again, we get the moment function as M of x, which is the integration of V of x, which will be MO multiplied by x minus A in singularity brackets raised to the power of 0. Next, we have an example of an uniformly distributed load with a magnitude of W0, which begins at point A. For this case, our loading example equation will be W of x is equivalent to negative WO multiplied by x minus A in singularity brackets raised to the power of 0. Note that WO is negative because the distributed load is pointing downwards, and through integration, our shear moment function is V of x, which is the integration of the loading function, which will be negative WO multiplied by x minus A in singularity brackets raised to the power of 1. And by integrating once again, we get our bending moment function also. M of x, which will be the integration of V of x, which is negative WO multiplied by x minus A in singularity brackets raised to the power of 2. Please be right with me, we only have 2 more examples to go through. Our next example is a concentrated force applied at location A, pointing upwards. Our loading function will be W of x, which is equivalent to PO multiplied by x minus A negative 1. Note that PO in this case is positive, not negative, because the concentrated force is pointing upwards. Through integration, we get our Vx equation as the integral of Wx, which will be PO multiplied by x minus A in singularity brackets raised to the power of 0. Integrating once again, we get our moment function as the integral of the shear function, which will be P of O multiplied by x minus A in singularity brackets raised to the power of 1. The final example we have is a distributed loading function at a slope defined by m. For this case, our loading function will be W of x is equivalent to negative m multiplied by x minus A in singularity brackets raised to the power of 1. Note that here in this case, it is negative m because m is a negative slope, not a positive one. Taking the integral, we can devise the shear force for this case as the integral of W of x, which will be equivalent to negative m over 2 multiplied by x minus A in singularity brackets raised to the power of 2. Integrating once again, we get our moment function to be the integral of the shear function, which will be equivalent to negative m over x multiplied by x minus a raised to the power of 3.
Next, we will be going through an example problem where we find the equations defining the shear and bending moment at any point along beam AB. Since the loading on AB is discontinuous, as can be seen by the triangular shape of the loading and the fact that it abruptly changes at point C, this question makes a classic case for using singularity functions in order to derive these equations. To begin, I'll be going over the strategy on how to approach the problem. The first step is generally solve for the reaction forces based off of the given loading and behavior of the pins. Furthermore, we should divide the total loading into a sum of two or more force distributions since the loading is discontinuous, and determine when each of the loadings begin so we can then devise the equation for loading using singularity functions. Finally, through the loading equation, we can derive equations for the shear and bending moment using integration. So our first step is to solve for the reaction forces. Now, based off of our prior knowledge in statics, we already know that since the loading is symmetric and there are no moments or other funky things going on, that the reaction forces at FA and FB will be equal. Hence, F of A is equal to F of B is equal to 1/2 F, which is the total loading. And we know the total loading is equal to the area of the loading diagram in the figure. And since it's triangular, it's equal to 1/2 BH is equal to 1/2 L times W naught. From there, we can derive that the reaction forces FA and FB are equal to 1/4 L W naught. This will be very useful to us moving forward. Our second step is to divide this figure into two or more independent loads. Now, one way to do it would be to cut it down the middle and just deal with A to C and C to B. However, one big problem with that is that now we're dealing with two discontinuous functions. Since from A to B and from C to E, the loading is discontinuous at C, since it abruptly ends and begins. A better solution would be to have one fully continuous loading and one discontinuous loading. That way, we're only dealing with one point of discontinuity that we can then only have one singularity function to deal with. That's what I will be doing. So one approach is to continue our loading from A to C all the way to B. And following the slope, since it's W naught at C, it'll be 2 W naught at B. And hence, our overall loading for the top is such. Now, to counteract the added load, we need to add a load from the bottom acting upwards. And since we know that the original loading at B is also 0, the loading at B for the downward force must also be negative 2 W naught, which is the same magnitude as the loading from the top. And we want it to start from 0 at C. Now we have two loadings. One at the top, which is continuous throughout the portion of AB, and one at the bottom, which is discontinuous, since it starts at C and then goes to B. Now that we have these two different loadings, we can derive loading equations for each of them, where we derive the loading as a function of the x, which is the distance from point A. For the top, since we know it's continuous, we can derive the slope as 2 W naught over L, since it is applied along the length of the beam AB, which is L. So thus, W1x is equal to 2 W naught over Lx. And then, we have the bottom loading, which is in fact discontinuous, since it starts from C. Now we can also find the slope for this loading, which is equal to negative 2 W naught over L over 2, or negative 4 W naught over L. However, since the loading starts at C, we need a discontinuity or a singularity function. So our function, W2x, would be equal to negative 4 W naught L, but we want this to start from C. So it would be x minus 1 over 2 L, where this is our Macaulay brackets and our singularity function. Hence, our overall loading function would be equal to 2 W naught over Lx minus 4 W naught over L x minus 1/2 L. Now, based off of this, we can derive an equation for shear. Now, as discussed previously in the background section, we know that the shear force is equal to the negative of the integral of the loading added to f of a, which is the reaction force at point A. Now, applying this integration, we know that is equal to negative 2w0 over L x minus 4w0 over L x minus 1/2 L in singularity functions times dx plus 1 over 4 W L naught. Now, integrating Macaulay brackets for singularity functions is the same as if there are brackets here, which means that this can be solved using just regular U substitution, which, when evaluated, is equal to negative WO over L x squared plus 2WO over L x minus 1/2 L squared plus 1 over 4 WL0. So this here is our equation for the shear as a function of x, where x is the distance from point A going towards point B. So now that we know our equation for shear, we can derive our equation for the moment. And our moment equation is just the integral of the shear function. And this is because we know that in the given figure, there was no moment at the beginning or at point A, so we don't have to account for any initial conditions, which is then, when evaluated, equal to just W0 over L x squared plus 2W0 over L x minus 1 over 2L squared plus 1 over 4 W0. Now, for time reasons, and since all of you already know integration, I won't be going over this entire step again, and I'll be writing down the answer, which is negative W0 over 3L x cubed plus 2W0 over 3L x minus 1/2 L cubed plus 1 over 4 W0 L x. This right here is our equation for the bending moment. Now, based off of this equation and the shear equation derived here, we can solve for the bending moments and the shear at any point along the beam. This is a very powerful tool for discontinuous loading. Thank you for listening.